Hi, so my name is Wu Jingmin. I am from Xiamen University, Malaysia, and if you can't already tell, we'll be discussing about the Lagrange remainder theorem today. So let's get to it. But before we get to the theorem, should introduce a few notions. This is the Taylor polynomial. It is a function that very accurately approximates various functions at a number x, what would be x naught. So when we look over at here in an example, you see that f of x is the exponent function e to the x, so it's just this blue curved line here, and then there is this strange other function which is t0 equals to 1. So what would you make of that? In actuality, this is a Taylor polynomial. It's just that it is for different finite number of terms. So this is 1, 2, 3, 4. So it's as you add the number of terms, you can see that actually the approximation gets pretty accurate. However, let's say I pause over here. Look, if you were to zoom in on this part here, you would get a pretty accurate approximation of e to the x. But look at all this surrounding it. It is a kind of error, isn't it? So what do we do about that? Like, how do we deal with this at all? Introducing the Lagrange remainder theorem, which states that let I be a neighborhood of the point x0 and let n be a non-negative integer. Suppose that the function f maps I to R has n plus 1 derivatives. Then for each point x does not equal to x0 in I, there is a point C strictly between x and x0, such that f of x is the following expression. So, what does this all mean? Well, f of x can clearly be split into two parts. Allow me to show you. So, first part is to be the nth Taylor polynomial, which we talked about earlier. And then there's also, in this case, the error, which is of this form. It is called the error of approximation of a Taylor polynomial, or also called the Lagrange error. So, if x equals to x0, what would happen? Well, our error would go to 0 and it would be case closed. We wouldn't have to care too much. Now, what we would like is that as n grows larger and larger, we would want it to have the error to go to 0, so that we get an accurate approximation. However, this is not always guaranteed. As you can see over here, in f n plus 1 derivative of c, as x changes, c also changes. If x is significantly larger than x0, our error will be much bigger. You could get lucky and the c over here, as you can see, makes it much smaller. But if x is really significantly larger, you will get a much larger error, and the error would not reach 0. That said, before we look at the proof, we have to acknowledge we will need something else. namely the Cauchy mean value theorem, which states for us very clearly, suppose that the function f maps I to R and g maps closed interval a b to R are continuous, and that their restrictions to the open interval a b are differentiable. Moreover, assume that for this case g prime of x does not equal to 0, and for all x in a b open interval. This automatically implies that there is a point x0 in the open interval ab at which f of b minus f of a divided by g of b minus g of a equals to f prime of x0 and over g prime over x0. So yes, we will be using this to do our proof. So what do we do first? Well, let, in this case, Pn of x equal to the Taylor polynomial, the nth Taylor polynomial in fact. And then what do we do next? We define a function, which will be rather interesting, of h of x equals to f of x minus Pn of x. So you can easily rewrite it as such, that the Taylor polynomial is on your right. So, what do you do next? Well, we take note that h of x actually represents our error, and that h of x has n plus 1 derivatives. We see this very clearly in the fact that both f of x and Pn of x have n plus 1 derivatives. So, what's next? We define g of x equals to bracket x minus x0 to the power of n plus 1. Now, why might we need that? Let's take a closer look. Now, note that if you put h of x0, if you just plug these in to h of x, you'll notice that it equals to 0. Now, why is that the case? Well, take a look at f of x and Pn of x. They both have the same order of contact. So, like it or not, they equal to each other for each derivative they take at x0. So, h of x naught to the nth derivative will eventually equal to 0. And g of x0 equals to g prime x0 equals to g double prime x0, and so on until g of n x0 equals to 0. How do we know that? It is actually simply because, look over here, you actually plug it in, it will equal to 0. So beyond that, what do we do next? Now, using the Cauchy MVT, we let a equals to x0 and b equals to x, because the Cauchy MVT actually demanded that we have an open interval a b, isn't it? As you can see right here. So, as you can see over here, we let a equals to x0 and b equals to x, and without loss of generality, we let x be larger than x0. The idea is simple, that we are thinking that this will not by any means be any different if you did it the other way around. Not much difference anyway. So let's use h of x over g of x. So what we end up seeing is that we can easily express it this way, because h of x0 and g of x0, both of these actually just equal to 0. So from here you can just use the MVT and find that the top is h prime x1 of x1 and g prime of x1 for some x1 that is in x0 and in x open interval. Now for h prime of x1 over g prime of x1, you can easily do the same thing, because the h of x0, h prime of x0 and g prime of x0 are both 0, so you're just minusing 0 on bottom and top. So by the MVT you have h double prime of x2 and g double prime of x2 for some x2 that is in x0 and x1. So for h of double prime x2 over g double prime x of x2, you can easily do the same thing, because h double prime x0 and g double prime x0 both are just 0 anyway. So then by the MVT you have h triple prime x3 divided by g triple prime x3. So then that's for some x3 that is in x0 to x2. So you can easily see that we can just keep doing that again and again until, well, h derivative n plus 1 derivative of c for some c that is in x0 to xn. Now we note that when you take the derivative n plus 1 of g and plug in c, you will get n plus 1 factorial. That's quite clear to see, given that if you look at the equation for g, which was a bit back over here, is very much easily you can tell. It's obvious. So then when you look at this, we now can just, and this is for some c that is in x0 to xn, thus we can conclude that h can be divided, h is divided by x minus x0 to bracket to the power of n plus 1 equals to f derivative n plus 1 of c with c divided by n plus 1 factorial. It was of course replacing this in particular. So then, and this is for some c in x not to xn. So then finally you see that h of x actually does equal to the exact error expression that we were looking for. So that completes our proof. Now for some interesting applications. First of them being the proof for the number e being irrational. We see in that proof, a proof of contradiction is used by assuming that e is rational and trying to see if it satisfies the properties of a rational number. That is just one of the few proofs and the uses of Lagrange remainder theorem. Now, there's also the fact that it can give us approximation for ln 1 plus x when ln when x equals to 1, which is at ln 2. For other values, we're well aware it doesn't work, but when it comes to x equals to 1, in fact the Lagrange remainder does converge to 0 for all these other values. So it does still work to some extent. And yes, it also helps us prove that a polynomial's Taylor polynomial is the polynomial itself, which is rather convenient when you think about it. Helps us to make sure that all our math is nice and tight. So just to think beyond this, take time to look and see more applications. Do you know of any? This is just to build some of your curiosity about mathematics. Alright, that will be all. Thank you for listening.